How's it going, guys? In our last video, we had a look at Chapter 6 of the computer science textbook, which is on computer systems. Today we're going to go into a very bulky but very important chapter and part of the course. This is computational thinking, algorithms, and data representation. So, before we get into the content itself, I'd just like to put out this disclaimer that the textbook goes into much more detail than this video. There's much more detailed examples and definitions of everything I cover here. It explains the processes of how to calculate various things. It's my recommendation that once you finish watching this video, you go back to the textbook, read over, and complete all the questions on these things, because there's some calculations here that you'll have to carry out, and there's certain things that don't really come across very well on a video, on a PowerPoint presentation. If you want, you can open up the textbook on page 144 and flick through it as we go through. So we'll start with the first part of our of the section, which is computational thinking. So computational thinking in general is a particular way of approaching a problem. It's very vague, but it's very important for computer science. And there are four key pillars of computational thinking. These are pattern matching or recognition, abstraction, decomposition, and algorithms. So you can see I've got definitions for all these here, and we'll go in depth on each one of these four pillars or concepts. These are very, very important to computer science. They're the foundation of computer science, effectively. So pattern matching. So we are recognizing patterns and finding out when two patterns are similar. So these patterns will recognizing patterns will save you time. It'll improve elegance, which we'll briefly touch on elegance later, and it can even create solutions where there were initially thought to be none. The mathematical formulas that you'll find in your log tables book, they were found and created when patterns were found, and therefore a formula could be created to find a common solution. So this formula can be applied to any problem of that specific type, and a solution can be found. An example of like pattern matching or recognition are car registration plates. So in Ireland, we follow a particular pattern or format for our registration plates. The first digits will always be the year the car was registered. The letter in the middle will represent the county that it was registered in, and then there's a string of identifying numbers at the end. So that's pattern matching, or pattern recognition, as you might see it be called. Next up, we have abstraction. This one's also very important. This is finding similarities between problems and discarding the differences and unnecessary details. You're abstracting, you're simplifying. You will have heard the term abstraction be used in abstract art, for example. It's not detailed, it's quite simplified, but you still know what it's a painting of. If you have an abstract art of a mountain, you still know that it's a mountain. You can still recognize that it's a mountain, and that's what abstraction in computer science effectively is. You're discarding these unnecessary details in order to get down to the root of the problem, the core problem. If we take an example, for example, a car, we could go out into a car park and find a car and say, that's a silver Toyota Avensis. But we can also just say that it's a car, and that would be abstracting, because if we need to know whether or not it's a car, we don't need to know the make, the model, the mileage, the technical specifications. We just need to know, is it a car? Yes, it's a car. Formula One cars possess more differences. Like they don't have a door, or they don't have like a roof, but they So they're not traditional cars in a sense. So we can sort of abstract them differently, but they can still abstract into a car. We can still technically call it a car. Abstraction then in terms of computing. If we're using a computer, we know it's a very complicated machine. Very, very few people actually know the detailed inner workings of a machine, but they can still use a computer. Most people out there who use a mobile phone have no idea how the processor works exactly, or how the Wi-Fi antenna works, but they are still able to use their phone to run applications and use the internet. So this is abstraction in practice and in the real world and in computing. So then the point of abstraction is to leave out irrelevant information and make our problems easier to solve in doing so. Here's a good example of abstraction in the real world. Baking a cake. You don't need to know the science behind the baking of the cake. You just need to know the basic details of a cake. So what ingredients do you need? How much of each ingredient do you need? How do you combine them? In what order do you mix them? How long does it go in the oven for? What temperature does it go in the oven? These are all the key important details involved in baking a cake. What you don't need to know to make a cake is what occasion is it being baked for? How does the oven bake the cake? How does it work? How does flour provide the structure for the cake? Those are unnecessary details. If you were tasked with baking a cake, you wouldn't need to know the answer to those questions to bake a cake. So this is abstraction in practice in the real world. In programming then, we can use things such as pseudocode, which are algorithms written in not actual code, but language very similar to code. You have probably written pseudocode before actually yourself to go through the steps of a problem. We can also, for example, if we're coding, we can use functions. So we can abstract the different aspects of a program into blocks of code, which we can define as functions. And that simplifies it down then into a few bigger sort of chunks, blocks. It makes it more manageable by abstracting, by simplifying. Also, HTML is actually, and CSS are a very good example of abstraction in practice in programming, because your HTML file will contain the course structure and the content of your web page. The CSS file will have all your nice fancy fonts, colors, and whatever else, but it's not necessary for the web page to function. You know, if you have an article that you want to get out to the world, you don't need CSS. It makes it look nice, but if you just want people to read what you've written, you don't need a CSS file. So that's just an example of abstraction. Then moving on to decomposition. So this is another important pillar or concept. This is breaking down a larger problem into smaller, more manageable problems. These pillars of computational thinking, you will have probably used these in practice before without even realizing them. We'll go back to the cake example. Ask yourself, what's involved in baking a cake? Break down the process into its constituent parts. So, okay, you need to buy the ingredients, you need to mix them together with the right quantities and in the right order, you need to place them into the baking tin, you need to preheat the oven to the correct temperature, you need to bake it in the oven for the correct amount of time, you need to take it out once that's done, and so you're breaking it down into these problems. This is effectively what a recipe is. You're breaking down the process into its constituent tasks, into its constituent parts. So here's an example from the textbook of a way we can apply decomposition to programming. So this is just the concept for a program to sort these particular strings into a particular order, where they should be in alphabetical order based on the first character. Where the strings begin with the same letter, they're sorted based on decreasing numerical order of the second character. So we can see here, we start off with this these strings here, these 5 strings. We have A3, F4, D6, H4, and F9. We sort these first in alphabetical order. So we have A, D, F, and H. And then our second step is where they begin with the same letter. We sort them by decreasing numerical order, which, as you can see, these 4 and 9 are increase in numerical order, so we swap those around, and that's our sorted string. But you can see here that this bigger problem was broken up into 2 smaller problems, and that's effectively what decomposition is. So now we're going to talk about algorithms. Algorithms are very, very important. This is a whole section in itself of this chapter. This is the second big section of this chapter, and it's also one of the 4 pillars of computational thinking as well. So in the real world, so what is an algorithm? Well, it's a sequence of steps to solve a problem, but it's not exclusively computer jargon. It's not necessarily computer terminology. It applies to real life too. So tying your laces is an algorithm that everyone knows. There are a series of predefined steps that everyone will follow to tie their laces. It's an algorithm. Or we can go back to the cake example that we've used twice prior. A cake recipe will give you the exact steps required to bake a cake. But if we need a chocolate cake, we can't use the recipe or algorithm for a plain one. So there's not really any recipe or algorithm that can be used to bake every cake, in the same way that there's not one algorithm that can be used to solve every problem. In computers then, there are 3 important aspects of a computer algorithm. So they have to possess clarity or unambiguity. So every single detail or possibility must be accounted for. Computers can't fill in the details if you omit something. You have to give them every possible detail. An algorithm has to have a limited number of steps so that it can actually finish and produce a result or an output. An algorithm with infinite steps will never finish, and it'll run indefinitely, and you'll never get a result. And it also must have a clear flow of control from the beginning of the algorithm to the end. When we're describing or writing algorithms, we can do it in many, many ways. I mentioned pseudocode earlier. We also have flowcharts, such as this flowchart here, to test if a light bulb in a lamp is working. So you can see the lamp doesn't work. Is it plugged in? No, plug it in. Okay, it is plugged in. Is the bulb burned out? No. Repair the lamp? Yes. Replace the bulb. So that's a flow chart of a real world practical algorithm. But we can also write our algorithms, of course, in a programming language such as Python, which I'm sure you will have done before. And we can also just describe our algorithms in a plain spoken language such as English, for example. Our cake recipe. See, it all comes together. We can then sort of mix our pillars together. So abstracting an algorithm, okay? We have a set steps for making a coffee, okay? But there are really sort of 2 main types of coffee that people might have or people might make. There's a sort of a barista sort of fancy coffee, or just an instant coffee that you might have in the morning at home before school. So for making an instant coffee, there's less steps, and therefore it's a less detailed algorithm, or a more abstract algorithm. Just boil the water in the kettle, pour into the mug, add the coffee powder, and stir, and you've effectively made your coffee. But with the barista coffee, there's more to it. There's more steps involved, and there's much more detail, and it's a less abstract algorithm. So you can see we've got all these steps, and these aren't even all the steps. Grinding the coffee beans, placing them in the portafilter, had to Google that word, turning on the machine, placing the filter in the machine, placing the mug under the filter, letting the water pour through the filter and into the mug, filling the mug with hot water. So there's much more steps involved in this coffee making algorithm. So this instant coffee algorithm is more abstract. Then when we're programming, we can use plain English, plain language, or pseudocode to represent the steps in our algorithm, so that we can understand exactly what we need to do and exactly what steps we need to take to solve the problem that we've been tasked with. So this then makes it much easier to convert this into a programming language, such as Python code. Elegance then, I briefly mentioned this earlier. This is simply just an algorithm being as simple and straightforward as it possibly can be. Okay, it's short and sweet in a way. It fulfills all the requirements in as little code as possible. It's clean, it's efficient, and yet it's functional. So that's what elegance is. Work and efficiency then. So in a future video, I'll touch on sorting algorithms. There are a few ones you need to know in the course, but there are a lot of sorting algorithms out there. But how do we know which one we should use? Well, we can judge them based off of how efficient they are. Now, of course, efficiency is how little work is done to achieve a goal. In this case, our goal is a sorted list. So how little work is done to sort a list. An algorithm should be designed to carry out as little operations as possible to achieve their goals in order to be as efficient as it can be. We can't really measure this efficiency in regular time, minutes, seconds, milliseconds, or whatever, since the speed of an algorithm is also reliant on the speed of the computer itself. A faster computer will run an algorithm in less amount of time. If you have a slow computer, it'll take longer to run the same algorithm. So how do we actually accurately measure the efficiency of an algorithm? Well, that's where time complexity comes in. So this is how long it would take for an algorithm to run given the length of the input n. The constants of these little equations are ignored almost always. It's only ever n, which is the input length, that's ever taken into account. So we represent time complexity through big O notation. So I've attached a graph here, as you can see, but I've also given the example of ON, okay? It's a linear function. Time taken to complete the algorithm is linearly proportional to the size of the input. So you'll have dealt with linear functions in maths. So this is very similar to that. We can represent these on graphs. As you can see, I've got a graph here that shows various time complexities. And we can sort of judge the efficiency of them based on these curves, these lines on this graph. So then we have equivalence classes. So these group together different algorithms that have the same time complexities. So ON, for example, right? If we have an input of length 1, right, it'll be linear, it'll be straight 1. It's that ON, it's less complex. It's constant time, so it's the same regardless of the input size. But ON squared is more complex because it exponentially grows. So you can see, even on this graph here, the input size, if we have an input of length 100, it'll be very quick to solve that. But if we enter in 1,000, suddenly it gets much, much larger. And even on the previous slide, you can see on versus on squared. You can see just how much longer it takes as we increase the input size. So these are equivalence classes, but why are they important? Well, we can use them. We can find out which algorithms fall within the same equivalence classes, and we can determine the difference between time complexity between different algorithms and different equivalence classes. So we group different algorithms together based on roughly how efficient they are. If they're of a similar efficiency or time complexity, we can group them into one equivalence class. So, but through equivalence classes, we can mathematically prove that an algorithm is in the best equivalence class it can be. So it's the most efficient. So ON doesn't get any quicker. You can't make that more efficient. That's about as efficient as it gets. Then we can also compare equivalence classes. So the growth of a function n and 2n would be relatively similar to each other on the graph. Likewise, the growth of a function n squared and 2n squared would be similar to each other. So we can group these two functions into two distinct equivalence classes, on and on squared. I understand that this is, especially if you haven't heard of this before, of course, it is very complicated. But if you turn to page 154 of the textbook, there's a nice visual representation of equivalence classes. You can see the lines on the graph for these different functions, and you can see visually the equivalence classes represented on the graph. Next, we're going to talk about heuristics. So heuristics is applied to problems that we can't realistically determine an answer for. There's problems such as the traveling salesman problem. This is a very famous problem. You can see I've attached a diagram I found here. So it's a problem where there's X amount of towns or N amount of towns. A salesman starts at one town, and they have to visit all the towns and get back to the town they started at in the shortest possible distance. Now, this is as you increase the number of towns, the N, it gets much harder to calculate the exact shortest distance. It's very difficult to solve, and it's stumped mathematicians for many years. So we use heuristics in this case, because while we can't find an exact answer, while it would be very difficult to find the exact answer, we can find one that's satisfactory, that's good enough, that's a reasonable guess, a reasonable estimate. So data representation then, this is our, I suppose, final big block here of this this chapter. I suppose we have two types of data. Continuous data, which is your analog data, and your discrete data, which is your digital data. We've gone over analog and digital multiple times before. We all know what they are. Most real-world data, such as sound waves, is continuous. It's analog and needs to be converted into discrete digital data so that a computer can actually use and process it. So in doing so, we make approximations of the data to convert it from continuous to discrete, which means that we can actually lose pieces of data from just approximating. For example, if we convert music from an analog format to a digital format, we lose some of the sound data through our approximation, which is why vinyl is still quite popular, because it's not digital and therefore contains all of the sound. But our discrete data is far, far easier to store and process by computers, so that's why we use it. And even with the sound, the data that is lost it's not noticeable to the human ear. So that's why we don't notice a massive disparity between, say, a song being played on a vinyl record and a song being played on, say, Spotify or Apple Music. Binary, then, we should know binary by now. It's a base 2 counting system. Okay, each one. So we have two values, a 1 and a 0, and each 1 or 0 is called a bit. Okay, there are 8 bits in a byte, 1024 bytes in a kilobyte, 1024 kilobytes in a megabyte, 1024 megabytes in a gigabyte, 1024 gigabytes in a terabyte, etc., etc. It goes on and on. Everyone is, I suppose, familiar with these units of storage for binary information. Anyway, if you're a user of technology, you will be somewhat familiar with what these are. So using 8 bits, which is 8 ones or zeros, we can represent 256 unique values, starting with 00000000, which represents 0, and ending with 11111111, which represents the decimal value of 255. So decimal is, to clarify, is the system we use to count. It's our base 10 counting system. We have 10 digits from 0 to 9. So we're going to convert binary to decimal. So let's convert the binary number 10010101 into decimal. So when you're doing this, you're going to draw this table here, okay? And this table is how you're going to carry out your calculations. So the top row here, right, we have 8 spaces here, and these are our place values, okay? These are powers of 2, right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7, okay? So that's what all these values represent, okay? 2 because there's 2 values, 1 and 0. So this is what these are. Then underneath that, we write our individual binary digits. So we can see this is our number 10010101. So we write that each digit in each spot, 10010101. So now we've got that done. It's a simple case of multiplication. So 1 by 1 is just 1. 2 by 0 is 0. 4 by 1 is 4. 8 by 0 is 0. 16 by 1 is 16. 32 by 0 is 0. 64 by 0 is 0. And 128 by 1 is 128, which gives us this list of numbers down here. Then we just add them all up and we get our decimal number, so 149. So that means that the binary number 10010101 converts to 149 in decimal. We can go backwards then from our decimal back to binary. So let's convert our 149 back into decimal. So we're dividing by 2. We're converting binary as base 2, so we're dividing by 2. Okay, so 149 divided by 2 is 74 remainder 1. Okay, so write down the remainder always in this. Draw up this table, write the remainder on the right hand side there. Then take the 74, bring it down, divide it by 2 is 37, no remainder there, so write down your 0. Then bring down the 37 again, divide it by 2, you get 18 remainder 1. Bring down 18, divide that by 2, you get 9, no remainder there. Then bring down your 9, you've got 9 divided by 2 is 4, with a remainder of 1, write down the remainder. 4 divided by 2 is just 2 with no remainder. 2 divided by 2 is 1 with no remainder. And 1 divided by 2 is, that should be a 0, but there's a remainder of 1. Then we read back up this way to get our decimal number. So 10010101, which is, if you'll remember, the number we started with. So that's binary and decimal, just very quickly. Then hexadecimal, then, this is a base 16 counting system. So, in our decimal, we have 10 digits from 0 to 9. In our binary, we have 2 digits because it's base 2, which we just have 0 and 1. Here we have 16 digits because we're also using the first 6 letters of the alphabet as digits as well. So this gives us 16 digits to work with instead of the usual 10. The biggest benefit of hexadecimal is that we can represent binary information with less digits. A byte, which if you'll remember is 8 bits or 8 ones and zeros, can be represented in just 2 digits in hexadecimal as opposed to the 8. So we have 00, which is just 0, and FF, which is 255. It's not necessarily used by computers in processing, but it's instead more so used by programmers to represent binary information and binary values in a more shorthand and compact format. So we're going to do conversion calculations again. Hexadecimal to decimal. We've got the hexadecimal number 54B or 54B. We're going to convert that from hexadecimal to decimal. So this is actually a very similar process from the decimal process. So we're going to draw up a similar table. You can see it's much smaller than the previous table. So our place values this time, because it's base 16, these are the powers of 16. So this is 16 to the 0, this is 16 to the 1, and this is 16 to the 2. Okay, and then like before, we just write our individual digits underneath these. So 5, 4, B, and then we multiply. But what do we do with the B here? We can't multiply B by 1. Well, B represents 11. Okay, so if we go back here, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11, 12, 13, 14, 15. So we can see we're just counting on. So if we have 9 here, then A represents 10, then B represents 11. So 1 by B is 11. Then 16 by 4 is 64, and 256 by 5 is 1280. Then we just, like before, we add up the bottom 3 values. 1280 plus 64 plus 11 is 1355, and that is what 54B is in decimal, 1355. Then back again from our decimal to hexadecimal. Again, this is very similar. It's a very similar process. It's just using 16s really instead of 2s. So we take this number, we divide by 16, you get 84, remainder 11. And remember, we know that 11 is B. So we say that the remainder is B. Then we take our 84 and we divide that by 16, and we get 5 with a remainder of 4. Then we take our 5, divide that by 16, and we get 0 with a remainder of 5. And like we did before, read backwards, read from bottom to top, and you get 5, 4, B. So our hex number is 54B, or 54B. So then we have ASCII, okay? This is a standard character set. It represents all the characters on an English keyboard with binary values. It encodes them in binary values. For example, lowercase a 0110 0001, which is 97 in decimal. And these binary values can be combined to create strings of characters and thus words and sentences. For example, here I've got hello world represented in binary in ASCII. So you can see each of these bytes here of 8 bits represents a single character in this hello world string. But then we have Unicode, which is much more advanced and has a lot more values than ASCII. It allows for many more characters than just the 256 that ASCII would allow. We can use it to represent characters from other languages that wouldn't use the Roman letters that we use, such as Japanese or Russian or Korean. It shares some of the character values with ASCII. The first 128 characters are actually the same in both formats, so in both ASCII and Unicode. But More characters means we need to represent more data, which means that we could end up using these massive binary values. So how do we solve this? How do we stop ourselves from transmitting unnecessary data and taking up unnecessary bandwidth? Well, we solve this with UTF-8 encoding. So this stands for Unicode Transformation Format, and the 8 stands for 8-bit. It encodes our Unicode characters, and it's also backwards compatible with our ASCII characters, which is one of the major benefits of UTF-8 encoding. It encodes our character values in either 1, 2, 3, or 4 bits, meaning the characters take up as little space as possible instead of always taking up 4 bits. It's the most popular encoding for websites, and it's widely used on the internet. And it stores characters as code points in hexadecimal in this format. So U plus and then hexadecimal value, in this case U plus 2713, which represents the little tick mark symbol here. There are calculations involved in converting these UTF-8 code points into UTF binary code. And these are detailed in page 165 and 166 of the textbook. It's too lengthy of a process to describe here, but it is in the textbook on page 165 and 166, and I'm sure there are other resources on the internet that will go more in depth on this specific process. Finally, we're going to conclude with a run over of data types. You should be well familiar with data types by now through your programming. We have our Boolean values, which are true or false, as we know. Integer values, which can just be a whole number, either positive or negative. We have a char or a character, which is just a single character, for example, this lowercase a. A string, which is just a series of characters, I suppose, strung together, hence the name, so like our hello world. Date, then, it represents a date, but it's not always present as a data type in most languages. Most programming languages, they wouldn't always have a specific data type, but it can be represented in a variety of ways in various programming languages. Then a float, which you'll be familiar with, a number with a decimal point in it, such as 24.2 or 111.563. Those are floats. Then lists or arrays, they're called lists in Python, they're called arrays in many other languages. They hold related data, and in Python, lists can hold a mix of data types, as you'll be well familiar with. So thank you very much for watching this video on computational thinking, algorithms, and data representation. This is a long chapter. It's certainly one of the longer ones, but it's also very important and contains many important concepts. But like I said at the beginning of the video, I highly recommend going through the textbook and doing all the questions on these ones and learning to carry out these calculations yourself and reading the examples for various things that the textbook provides, because it's a good resource here. And I hope this video helped somewhat. In our next computer science video, we're going to be going over chapter 8, which is software development, which goes over various aspects of the software development process and design and the different stages of software development and such. So that'll be in our next computer science video. But for now, I'd like to once again thank you very much for watching, and good luck with the leaving.